Welcome to the demo of our project demonstrating CavePI, autonomous exploration of underwater caves by semantic guidance. Underwater caves provide valuable knowledge of hydrology, geology, archaeology, and marine ecology. However, exploring underwater caves is a hazardous and labor-intensive task for human divers due to their complex geometry and lack of natural light. Human divers lay a continuous line, known as cave line, from entrance to exit of a cave for navigation guidance. Other navigation markers include arrows and cookies that informs about exit direction and presence of other divers, respectively. A remotely operated vehicle or ROV can safely and efficiently navigate inside caves using these markers. However, they rely on continuous input from human operator, making them unsuitable for long-term exploration. Capabilities of ROVs are also limited by communication latency, lack of sensory feedback to operator, tether length, etc. Therefore, we envision an autonomous underwater vehicle, or AUV, that is able to perform guided navigation by leveraging the semantic information from the surrounding environment. In this paper, we introduce CavePI, a novel AUV capable of navigating inside underwater caves using caveline and other markers as semantic guides. Specifically, we present the system design, visual learning methods for semantic perception, and motion control algorithms for visual servoing. The perception and control accuracy is evaluated by extensive experiments in a laboratory setup. We also develop a digital twin of CavePI in Ross gazebo environment for prototyping and refinement. Finally, CavePI is deployed in diverse real-world environments such as spring water and natural underwater caves to validate the robustness and its capability to perform long-term autonomous missions. CavePI is designed as a compact, one-person portable and deployable vehicle. The single enclosure contains sensors, single-board computers, flight controller, battery, etc. Specifically, we use a Raspberry Pi 5 for motion planning and control. The other computer, Jetson Nano, offers GPU-accelerated computation for accurate semantic segmentation. A Pixhawk flight controller operates the thrusters and monitors telemetry data. Images from down-facing camera are used for cave line detection and tracking. Among the 4 thrusters, 2 are used to control planar motion, while the other 2 control vertical motion. A down-facing sonar is attached to provide depth measurement. A clear dome is attached in front of the robot that houses the front-facing camera. This camera is used for diver-robot visual communication and other servoing tasks. The line tracking performance is initially evaluated in a laboratory water tank. A line is laid on the tank floor in a rectangular shape. As shown here, CavePI successfully completes multiple loops without losing track or hitting the tank walls. The bottom right view shows the segmentation map overlaid on the raw image. The farthest segmented contour is selected as the next waypoint. The blue arrow shows the heading angle with respect to the robot's longitudinal axis. We also develop a ROS-based digital twin of CavePI. It resembles the sensors and other physical attributes of the actual robot. The twin model is deployed in a simulated underwater environment in gazebo. To mimic cave lines, we used thin cylindrical structures and laid them in different shapes. The simulation platform allows extensive testing and fine-tuning of CavePI's control system before real-world deployment. Following the tank experiments, we deploy CavePI into open water springs for real-world testing. The line is laid on the uneven riverbed in irregular shapes that features obstacles, vertical variations, turns, loops, etc. Moreover, flickering light and caustic effects create visual distortions that could challenge perception. Yet CavePI's advanced perception module proves its robustness, successfully recognizing its path despite these conditions. As the robot moves through the spring, it encounters strong currents that push it off course, especially when navigating upstream. This example shows CavePI struggling against hydrodynamic forces, but eventually overcoming it without losing track of the line. Finally, we deploy CavePI in underwater caves that has no natural light. Here, in one of the most hostile and challenging environments, CavePI shows promising results for long-term autonomous exploration in GPS-denied, feature-deprived conditions. The extensive in-house testing and real-world missions reveal several engineering challenges and limitations of CavePI. Due to its slightly back-heavy design, the robot tends to pitch upward when navigating upstream. This example shows CavePI struggling to turn against the current at a corner, eventually losing track of the line. To address this, we are developing more advanced nonlinear control systems that will account for hydrodynamic forces. The strength of water current is evident from this clip, as it pushes the robot backward, even though it is trying to navigate forward. In this low-light scene, the thrusters disturb the slits on the ground, making perception even more difficult. Eventually, the robot loses track of the cave line. Looking ahead, the next iteration of CavePI will feature enhanced hardware, more accurate perception, and a more robust control system. Please refer to the project page for more details. Thank you.